This is MCO2. Um, this is about different kind of sorting algorithm wherein we are required to implement the three n squared sorting algorithms: bubble sort, insertion sort, and selection sort. Also, we are required to implement two n log n sorting algorithm. For this instance, I've implemented merge sort and quick sort. As for the data requirements, we are required to have different types of data that will be used for the sorting algorithms. The first type is random, wherein the the random data is wherein the integers in the file or the input is randomly ordered. And I'm using the intervals 3, 5, 7, and 10 to properly plot them in for the growth chart later. So that's the um, random type of input data. And another variance of the input data is descending. Wherein for the descending, I'm also using the same interval 1, 3, 5, 7, and 10,000. But for the descending, the integers in the input is they are in arranged deliberately arranged from high to low. So all of these are arranged from high to low. The last type of data that we will be used is almost sorted, wherein 90% of the integers are properly sorted in ascending order, and the last 10% is randomly sorted. So for this instance, for this first interval 1000, the integers are properly sorted from 1 to 900, which represents the 90% of the 90% of the total 1000, and then the last 901 to 1000 is randomly sorted. So the randomly sorted part is at the end of the input, and it's the same for the almost sorted 3, almost sorted 5, 7, and 10. So how all these input files will be used and will be fed onto this different algorithm, and will be plotting their growth chart using frequency count as the y-axis, and using the size of the input, this interval, as the x-axis. So we will be starting off with the n squared sorting algorithms. For how we use these input files in the sorting algorithms is that I just have to uncomment um these input files based on what input files I need to run. So I've already actually run all these input files against all these algorithms here, and I've already plotted the the output of sorting each sorting algorithm. I'll discuss first the findings for the n squared algorithm, bubble sort, insertion, and selection sort. So for instance, if I'll just try to rerun this to demo the program. I'll just rerun the bubble sort using the almost sorted um, data input. So this is just a sample output wherein the program will output what is the type of input used. So it's almost sorted, and then the frequency count calculated after running each of the input file interval. So it's gonna be the same for the other n squared algorithm, like in insertion and selection sort. They share the same behavior on how you change the input file on whether what you want to run for each input type. So if you I have this three sheets in Excel where I plotted the different n squared algorithm and recorded their frequency count based on the input, which represents the same interval we used for the different size, different number of integers in the input file. So for the n squared algorithm, for the randomly typed data, you'll see here that somehow selection sort is performing better for the randomly generated data, given the computed frequency count according to the sizes. And based on while bubble sort and insertion sort, they share the same frequency count, hence they also have the same um, plot in the graph. But you can see here that regardless of what kind of n squared sort, you'll see here that um, all all three sorting algorithms shows that the frequency count grows as the input size or the n grows as well. So it's consistent for all the three sorting algorithms for the random type data. And again, selection sort somehow perform better based on frequency count compared to bubble sort and insertion sort. Now, moving on to the next type of data, which is the descending, wherein we deliberately sorted the integers from high to low and then run the program. So I'll just run it for demo purposes in bubble sort. So it will just behave the same, but we'll use different input data. And this time, this is for the descending input data. So you'll see here that it is now using the different variation of our data, the descending, and then it still output the frequency count after each processing of the file that varies the the size of n. So if you plot the the growth chart for the descent for the 3n squared algorithm using the descending data type or the reverse, you'll see here that it's still the same. We're in it's still the same that as the size of n grows, the frequency count grows as well. And here you'll see that still selection sort is performing better compared to bubble sort and insertion sort for the reverse or for the descending kind of data based on my computed frequency count. And again, they still share the same behavior of as the n grows, the frequency count grows, and bubble sort and insertion sort performing the same. Um, yeah, that's for the reverse. This is how the sorting n squared algorithms behave for the reverse or descending data type. For the last one is the almost sorted, wherein the 90% is properly sorted, and the remaining 10% at the end of the input is randomly sorted. So after feeding this input in those n squared algorithm, this is how they behave. This is the almost sorted 90-10. So what we can see here that yeah, still consistent that as the n grows, the frequency count grows with it. And you'll see here that still bubble sort and insertion sort perform the same, while selection sort is by far performing very well still for the almost sorted kind of input data. And still for the almost sorted 90-10 data, you'll see that as the size of n grows, the frequency growth as well grows as well, and it's consistent for the 3n squared sorting algorithm. Now moving on to the n log n sorting algorithm. For this instance, I've implemented quick sort and merge sort. So similarly to the n squared algorithm, they share the same behavior on how I change the input file here. So let's just try to, for demo purposes, I'll run the quick sort algorithm using the almost sorted input file. The same input is used for the n squared and the n log n algorithms. So if I run this, yeah, it will still um, output the frequency count per file here. So I've already run all these different input files for the quick sort and the merge sort. So for demo purposes, I'll run the random in the merge sort to see the sample output. But it should be consistent since I'm using frequency count and not the runtime as a measurement on how the sorting algorithm performs. So I'm running all the random data type, random randomly arranged integers as input for the merge sort. So you'll see here that the merge sort program will still output the use input and the computed frequency count. Now, if you run all these types of the input file, the random, descending, and almost sorted for both quick sort and merge sort, and plot them to see the growth chart, the result is for random, for the n log n algorithm, quick sort and merge sort. Um, you'll see here that the quick sort performed better than the merge sort for the random type of data. But yeah, it's still consistent behavior that as the size of n grows, the frequency count grows as well. But if you compare directly the computed frequency count, you'll see here that the quick sort, it performs better in all input size, the size of n compared to merge sort for randomly ordered integers. Now for the reversed or descending data, the result is that it's it's the it's the other way around. This time for the reverse or the descending data, merge sort performs better than the quick sort based on the computed frequency count, but still it's consistent. It's actually outperformed by um, largely compared to quick sort for the descending data. And still the same behavior for the n log n, like the n squared algorithm, that it is consistent that as the size of n grows, it's computing the size of frequency count grows as well. But you'll see here the big difference between the merge sort and the quick sort frequency count for the reverse or descending data. Now, lastly, for the almost sorted, for the n log both the n log n algorithms, quick sort and merge sort, for the almost sorted data, merge sort again outperformed the quick sort um, significantly based on the computed frequency count here. Um, Again, still the same behavior that the frequency ground grows as the size of n grows. So after running the random reverse and almost sorted, the result shows that quick sort will outperform merge sort only in the if the data is randomly sorted. But merge sort will outperform quick sort for the other two types of data for the reverse and for the almost sorted based on the computed based on the computed growth chart. And yeah, that's the end of demo for MCO2.